Let us recall what we have did in the previous lecture. In the previous lecture, we have defined a closure of a set. So what is the closure of the set? If X is a metric space and A is a subset of X, a closure of the set is denoted by A closure or A bar is equal to A union D of A. What is D of A? A D of A is the set of all limit points of A. So this is the definition of the closure of a set, and we have seen some examples related to it. Then we have discussed the boundary points or a boundary of the set. Boundary of a set. So boundary of a set is a set of all boundary points. It's called the boundary of the set, and it's denoted by boundary or B dr of A. What is the set boundary points? If I want to say X is a boundary point, or I can say what is this set represent? It is a set of all points in X such that for every r greater than 0, SR of X intersection with A is non-empty, and SR of X intersection with A complement is non-empty. That means if you draw a neighborhood of X, any neighborhood of X, it always have intersection with A and A complement. Then that point is called the boundary point, and set of all those points are called the boundary of a set. We also have seen the examples related to it. We also discussed the Cantor set, and we have proved that the Cantor set is a closed set. And then we have discussed some related examples or theorems related to the closure. The first thing we have proved that A bar is always a closed set. This is the first result we have did. The second result we have did that A is closed if and only if A is equal to A bar. This is the second result we have did. The third note we have observed that A closure is the intersection of all the closed set, all the subsets of X, where F is closed and F is a superset of A. This is the node, or I can say the A closure is the smallest superset of A which contains all closed sets, which are supersets of A. So these things we have discussed in the previous lecture, and also we have talked about the interior of A is a subset of A, and which will be the subset of A closure. This is always true. And afterwards, I am giving you some exercise to deal with, to prove it. What was that exercise? That exercise is this. Let X be a metric space and A is a subset of X, B is also a subset of X. Then prove that A closure is this. A closure can be represented in this manner. Interior of complement is a closure complement, and all other properties or all other results that we have done or I gave you into the exercise. So how many of you have done any of this 7 exercise? Anyone has have tried for this exercises? If you want to know this subject, then you have to try for this various exercise, and then and only then you are able to recall the results you have to remember the results, you need to apply the definitions. When you will apply the definition, when you will try, otherwise you will not learn this subject. Okay? And if you will not try, then every definition is mixed up. When you have to pick up every, or when we have to pick up some, that confusion always will be there. So it is better that you can apply these results which we have discussed many a times. For that, you have to solve main exercises. Let us try to prove the first one. It says that a closure is actually this set. So here I want to show that two sets are equal. So I'm picking one point into the a closure. So if x belongs to a closure, then this will implies x is belongs to a, or x belongs to d of a. But what does that mean of a d of a? It is a set of all limit points of a. So I can say that x is belongs to a, or x is a limit point of a. Now there will be two cases. If x is belongs to a, or x is a limit point of a. One of the situation is possible. So if x is belongs to a, then definitely we have xr of x intersection a, because xr of a x we always contain x, and x is belongs to a. So this intersection is always a singleton point. So that's why this is non-empty, because SR of x is always contain center. Okay, and a is always already there. So that's why this intersection is non-empty. Now if x is not in a, if x is not in a, that means x will be a limit point of it. So as per the definition of a limit point, what we can say, therefore, for every r greater than 0, for every neighborhood, SR of x minus x intersection A is non-empty. But x is already not in A. X is not in A. So whether I write down here or not write down here, it will not make any difference. So that's why this statement I can write down as, for r greater than 0, SR of x intersection with A is non-empty. So what I said is x is not here. So if I include here in this set, then it will not make any difference. So that's why this statement we can write down. So in any of the case, either x is in A or x is in not in A, this x is satisfying this situation. So we can say that x is belongs to, all x belongs to x such that SR of x intersection with A is non-empty for every r greater than 0. Why the other side is true? That means if the point is here, why we can say that it is in closure? So now, if x is belongs to that set, then why we can say that it is in closure? It is, I think so, it is clear that it is x belongs to a closure. I want the answer why. I want the answer from you. If you are not giving now, I am not giving the answer to that. try, you can see and tell. The same argument which you have did it here. Why you guys are okay? Fine. I'm not giving you the reason for that. You can try for that yourself. The second exercise is this. That is interior of a complement is equal to a closer complement. So let us try to do the second one. So we have to prove that interior of a complement is a closer complement. So I have to show that two sets are equal. So it is to prove that if I pick up any point here, how to show that that point is also here. So let X belongs to interior of a closure. This will implies it is an interior point. So I can say X is an interior point of that. And according to definition of interior point, what we can say, there exists R greater than 0. That means there exists some neighborhood of X, which is SR of X, which is a subset of a complement, such that we can write this due to the definition of interior of a complement. Now, what is the situation? The situation we already discussed in previous one of the lecture. You can, I'm just drawing that same figure here. Now, what is the situation? This is the set A, and this SR of X is a subset of A complement. That means SR of X is here outside this. So this statement will gives you there exists R greater than 0 such that SR of X intersection with A is non-empty. According to this definition, which we have discussed, the first statement. The first statement has tells you that A complement is actually the SR of X intersection A is non-empty for every R. What will be the negation of this statement if it is not any point which is not in A closure? That means this there exists some R for which this intersection is phi. So exactly the same thing we got here. There exists some R where this intersection is phi. So this will implies X does not belongs to A closure. If it is not in belongs to A closure, we can say it is in complement. So that proves this. What about the converse? That means if I pick up one point here, I have to show that that point is here. But that will follows by the converse argument if we do the same thing. So if I have a point here in this, then I can write down that is not in A complement. If it is not in A complement, again by using the first result, we can say that there exists some R greater than 0 such that SR of X subset of A, which is phi. And by the same argument, we can say that this thing. And so we can say that X is an interior point of A complement. And so we have this. So instead of writing implies, we can write as double implies. So that will prove the second statement. How to prove the third statement? Into the similar manner, you can able to do that. So let us write the second statement. What we have to third statement, sorry. So the third statement says that we have to prove that A closure is X minus interior of X minus A. This is the problem. So I'm trying to prove with some another things. These are many ways to do this. One example, you can prove it by many ways. So I will take one point X which is not in A closure. So this will implies if it is not in a closure, by exercise 1 we can say that there exists r greater than 0, SR of x intersection with A is phi. That means there exists some neighborhood such that that neighborhood with A having no point as a common. And this will implies there exists r greater than 0 such that SR of x is a subset of A complement, again by the previous argument which we have did here. So what does it mean? This will implies there exists r greater than 0 such that SR of x is a subset of interior of A complement. Can we say this? We can write for every point which are in x, which are interior point of that. So we can write this. Or I don't want that. Actually, I need that x is belongs to interior of that. So this is actually gives you, therefore x is belongs to interior of A complement. So I will require this. But what is this statement? This says that x minus interior, and I've started with x is not in A complement, sorry, A closure. So this will gives you x is does not belongs to x minus interior of x minus A. That is the complement. So that proves that if x is not in here, we have proved that x is not in here. So we have proved that this which will be subset of this one. Conversely, the same argument will follows the things. If it is not here, that means we can say that it is. So it is implies this is the there. If it is an interior point, for there exists some r greater than 0, we can have some neighborhood of that which is subset of A complement. So this is also implies this. And by the same argument, this will implies this. And so we have this. So finally, we can have this statement: A closure is x minus interior of x minus A. That proves the third statement. What was the fourth statement? It says that the boundary of A is A closure intersection x minus A closure. That means complements closure. Or I can say closure minus interior of A. This result actually you can prove from the third, using the third argument. So what we can, so this result, I'm talking about this one. This is equal to this one. You can use the third argument. You prove this. Let us try to prove that boundary of A is the intersection of closure and its complement closure. So to prove that, so what to prove, let us write that. You have to prove that the boundary of A is equal to A closure intersection x minus A closure. That is a complement closure. So I'll start with some point in boundary of A. So if it is in boundary, as per the definition, what we can say, for every r greater than 0, SR of x intersection with A is non-empty, and SR of x intersection with A complement will be non-empty. But as per the definition of, or as per the exercise 1, what was the exercise 1? We have proved that A complement can be written as SR of x intersection with A is non-empty for every R. So if you use that one, this first statement will gives you X is belongs to A closure, and the second statement will gives you X belongs to a closure, a complement closure. So that will gives you X is belongs to A closure intersection X minus A closure. That proves that these two quantities are equal, because this is also true for if and only with the same argument. Now let us try to prove that. Now what is the next target is to prove that boundary of A will be A closure minus A interior. We will already have proved this, so let us start with that. So boundary of A is A closure intersection X minus A closure. Now here in the second quantity, and we use the previous result which we have did, A closure is equal to what we have proved here is X minus interior of X minus A, that is X minus interior of X minus A. This we have done in the previous one. So we will replace this here A by X minus A. So if I replace A by X minus A, this will be X minus A complement. This is X minus interior of, instead of A we have X minus A, so it is a complement of complement, so that will be A. So what is X minus A closure is X minus interior of A. So that value I can write down here. So this is actually equal to A closure intersection X minus interior of A. What is X minus interior of A? It is A closure intersection interior of A complement. What is the definition of A minus B? The A minus B is exactly same as A intersection B complement. So it is the same thing we have here. So hence this is A closure minus interior of A, which proves that the second, that boundary of A is closure minus interior. This is also notation for interior. This is also notation for interior. So if you will not confuse yourself with that notation, you just write down this is, both the things are same. Fine. What was the next things we have to do? The next thing is closure is the set of all points where the distance between point and a set is 0. So distance between point and a set is 0. If you collect all those points, then that will become closure. Okay. Now to prove this statement, let us do the fifth statement. What to prove is this: A closure, X belongs to X, the distance between X and A is 0. This is our objective. So assume that this distance between X and A is epsilon or greater than 0. If it is epsilon, if this distance is epsilon, then what will happen? This will implies X is neither in A, and so what is the situation I am talking about? Suppose this is your set A and there is a point x which is outside, and the distance between these two is epsilon. So I will try to draw a neighborhood of this point x which having the radius epsilon by 2. So this epsilon by 2 I am taking a radius. So definitely if I have such, if I am able to draw such neighborhood, then the intersection with that neighborhood with A is empty. So I'm picking that minus x, intersection with A is phi, that we can say. So this will imply x is not in A, and this gives you x is not a limit point of A. So this will imply x is not in A union D of A. But what is this? It is actually A closure. So if you have assume that the distance between x and A is some epsilon, that means you have assumed that x is not in this set, then it is not in closure. And conversely also we have the same thing. If it is not in closure, then we can say that x not in this. Then we can say that x is not in A and x is not a limit point. If it is not in limit point, we can say x is not a limit point, and we have this. And so the distance between these two is greater than. So we have this. Now we can able to write this. Now using this exercise, I am giving you two more exercise to do it yourself, to prove by yourself. The first exercise I am giving you is prove that using this result, prove that singleton set is closed using result 5. This. So I can write this is A. The B also you can write prove that any finite set is closed using result 5. You will prove this two things. Using this result, you can prove this two statement that singleton set is a closed set, and using that concept, you also can able to prove that any finite set in a matrix space will be a closed set. Okay. Now next thing is this: A is closed if and only boundary will contain in A. Let us try to prove that. The sixth statement to prove is A is closed if and only boundary of A will contain in A. This is the thing you need to prove. Using the previous result, one of the quantity or one of the things which is trivial. Which one is trivial? So suppose that this A is closed implies this boundary of A is subset of A is very trivial. Why? I can tell you. A is closed. Suppose that A is closed. If A is closed, then we know that it is implies A is equal to A closure, which we already proved. And this will implies A equal to, in the previous statement we have proved that the boundary of A is a subset of A intersection x minus a complement or closure of x minus a. So if you use this one, this result, we can say that using previous result, we say that the boundary of a, which is equal to a closure intersection x minus a closure, but a is closed, so we can say that this is a subset of x minus a closure. So I can say this is the subset of a. So hence boundary of a is always a subset of a. That proves the one side. Let us try to prove the other side. That means the boundary of a is a subset of a, then a is definitely closed set, which also can be proved using the previous results. Okay. So suppose that the boundary of a is subset of a. We know that, or we know by previous result actually, the boundary of a is equal to a closure minus a interior. Interior, for the interior we have notation is interior of a. This is the notation for interior we have used. So now I'll start with this. A closure minus interior of a. I'm picking union here. This quantity. As per this argument, so what we can say is, I'm okay. So we have this. Let me write that step. Huh? We have this boundary of a is a subset of a, and if I use this argument, then this will be closure minus interior of a will be subset of a. And if I make union both side with interior of a, then this is a closure. What I want to prove, actually a is closed. So if I can prove that a closure is subset of a, then a will be a closed, because a is always a subset of a closure. So I can able to prove that a closure is equal to a. So this is always true. I want to prove that this closure is a subset of a. So that is my objective. Since this is my objective, I want to that this a closure is there, so I can remove this a interior from this. So for that I am adding that. Now in the set, when I say it is add, you make a union of that. Union of interior of a intersection a union interior of a. But what will be this gives? A closure minus interior union interior. This will gives you a closure. And what is this will gives you a union interior of a. Interior of a is always contained by a. So union of, so this is the things we always we have. Interior of a is always a subset of a. So this is again a subset of a. So actually this is equal to a. So that's why this is, we have a closure is a subset of a. So therefore a closure equal to a, because a is always a subset of a closure. Hence a is closed. And that proves that if the boundary of a is subset of a, then a will be a closed set. What was the next result? The next result is for a union b closure is equal to a closure union b closure. Okay. So we have to prove that this thing. This is the seventh. A close A union B closer is equal to A closer union B closer. So there are two sets. We have to prove that one of them is a subset of other. One side is very trivial. Why? Because we know that A is a subset of A closer and B will be a subset of B closer. So therefore, what we can write, A union B will be a subset of A closer union B closer. Here I am going to use this result actually, that A is a subset of B, that will implies A bar is a subset of B bar. If you don't want to use this result, what we can say, that A bar is a closed set and B bar is also a closed set. So the union of a closed set is a closed set, that we already proved. And what is A union B bar? A union B bar, what is the smallest set which is a superset of this A union B, which will be a closed set? So the smallest superset of A union B is A union B closer, and this is also superset of that. So hence we can say that A union B is a subset of A union B closer, and this will be a subset of A union B closer, if you don't want to use this one. So what is the argument here we have to give is A closer union B closer is a closed set, and A union B closer is the smallest closed superset of A union B as per the property of closure. It is the smallest closed set which is a superset of set itself. So that's why we have this. So that's why this A union B closer is a subset of A closer union B closer. Now the converse means this will be a subset of that, which is also very trivial or easy, we can say. Where we have used this result, A is a subset of B implies A closer will be a subset of B closer, that we can use here. Why? Because A is a subset of A union B and B is always a subset of A union B. So this will implies A closer is a subset of A union B closer and B closer is a subset of A union B closer. So this will implies A closer union B closer is a subset of A union B closer. So if I call this is a statement 1 and if I call this is as a 2, so from 1 and 2, we get A union B closer is equal to A closer union B closer. Obvious question one can ask, what about the intersection? That I'm giving you as an exercise. You can try to discuss that by yourself.
Excuse me, sir.
Yes.
Sir, you said A union B closure is the superset of A union B, but you have written that A union B का closure is subset of A union B.
No, A union B
Sir,
closer
here.
smallest closed set which is a superset of A union B. So A union B का superset
सर superset है ना
closure,
A union B का closure.
which will be the smallest one. This is already, this, see, this A closure union B closure is the superset of A union B. But what will be the smallest closed set, which is a superset of A union B, which is A union B closure. So that's why this A union B closure has to be in between these two.
So but it is the superset of A union B.
हाँ, तो A union B closure is a superset. So ये superset नहीं हुआ. A union B is a superset. So this is the superset.
Okay, sir.